So we're going to talk about some additional examples for importance sampling, okay? Additional examples. All right, and we're going to use some examples, right? The example that I'm going to use is example 1, okay? Let's suppose we want to integrate the following. All right, so this is a tail probability. All right, so basically you want to integrate this a is some value between 0 and 1, right? Okay, so of course this integral is very easy to evaluate, right? So if you just you can just do by hand, right? Okay, I just leave that out. Okay, so it's easy to do by hand. Now we want to get a Monte Carlo estimator for this integral. Okay, the usual way that you would proceed is like this. Okay, so you basically write it as such. Times 1, okay? So 0 to 1, right? So you change the, so this one is your h of x, and that's your fx, okay? Your fx, you use a simple uniform density, all right? Now you have this simple uniform density here, and then this is an indicator function, right? So this, it means 1 if x is greater than a, and means 0 is if x is less than or equals to a, all right? So basically when you have this, right, for any values that's below a, so this will be 0, okay? So this is just another way of writing that integral, okay? If you sketch out, right, basically this is what you want. This integral, it looks something like this. It has a maximum somewhere. So maybe something like this, and then it comes down again, right? So you basically want, depending on where your a is, you basically want this integral, right? So this integral is the same as having this integral. So you have a flat line over here until a. This is all flat. And then you come over here, then you have a curve, right? So it's the same, right? Okay, so they're actually the same, okay? So this is just another way to look at it, okay? Now, once you write it like this, you can actually express it in terms of the expectation, right? So expectation of x squared, 1 minus x, then indicator function x greater than a, right? Where your x is uniform 0, 1, right? And therefore your Monte Carlo estimator will be just the sample mean, okay? Xi other than a, right? Where your x1 until xn are IID uniform 0, 1, okay? Now, this estimator has a kind of a problem, which is if you sample from, so if you sample, let's say I superimpose a uniform, right? Suppose, let's say this is the uniform, okay? Okay, somewhere like this. Okay, this is the uniform. Fx equals to 1, right? For example. The problem is that for any values less than a, right? The moment you sample any values below a, right? This will be 0, okay? So you end up over here, you're gonna get a lot of zeros. Maybe this will be maybe 0.9, 7. So suppose your a is 0.8, right? And so on. So of course you have your x is larger than 0.8, and then you sub in everything, right? So this, it could be something less than 0.8, right? So maybe 0.64, something, right? The thing is, you will get a lot of zeros here, right? So in terms of the distribution of the simulated values, what you're going to get is you're going to get a whole bunch of zeros here. And then these are the other values, right? So the other values might be distributed something like this. Okay. So of course, when you average them, right? So when you average them, you might actually get the value that is actually close to theta, right? So your theta hat is actually unbiased for theta. The problem is the spread of the data, because there are so many of them in 0, right? So the variance tends to be very large. Okay, so this method is actually not very good. It's very simple, but it's not good because the problem is the variance is too big. Variance of this is high. Okay, so we don't actually want that. All right. Okay, so then we need to come up with a different way to do this. So the way we're going to do this is to use importance sampling. All right. Now let's watch carefully how importance sampling overcomes this problem. Okay. Now I'll just erase this part. Okay. Maybe I'll just write it down somewhere. Select. Select. Never mind. Okay, so I just maybe write down my Monte Carlo estimator somewhere here. By the way, you use capital letters for when you write down the estimator, okay? Because it's the general form, right? This is a capital letter, right? The small letter is reserved when you actually have a sample. You actually have a realization, right? You collected the data, then you replace it with the small letters, right? Okay, that's just a notation for appropriate notation writing, okay? So let me just erase this. All right, so we look at it from another point of view, okay? So now this is hx and fx, right? So I'm going to write it like this. X squared 1x, okay? X greater than a times 1, okay? Now, I will find some gx now, right? So this is my fx, that's my, sorry, this is my hx and this is my fx, okay? I find a gx, now when I find a gx, right, this gx has to be the distribution of this gx has to be as much as possible, try to make it similar to the distribution of f of x, okay? So the most reasonable candidate here, your fx is uniform, right? So you should pick another uniform candidate, okay? And there's just a very nice candidate here, right? So you only want to integrate values that start from a to 1, okay? So a natural candidate is to pick a uniform random variable over the interval a to 1, okay? That would be falling in the same family as the uniform distribution. It's just that the left limit of the interval is not 0, okay? But they are related, all right? That usually will work. So you want to find a uniform a to 1. So the density is very easy, right? So this is your a, this is your 1. So the length here is 1 minus a, right? And therefore your height here is 1 over 1 minus a, right? Because the uniform is just a rectangle, right? Okay. So here your density of your gx is 1 minus a. And therefore you multiply this with 1 minus a, right? Gx, sorry, it's dx, okay? This is of course your gx. And by writing so, you can write your expectation as x squared. So of course this one is also over, all right? 1 over 1 minus a is when your x is greater than a, right? Other than that, it is actually 0, yeah? Okay. So you can remove this 2, right? Since they are all, their support is greater than a, right? So 1 minus a, 1 minus x. This is divided by 1 over 1 minus a. So you move it out, it goes, it's a constant, so you can take it out like this, okay? Where your x is now uniform a1. All right? Okay, so just now, so we look at another way to okay, we looked at another way to evaluate this integral, right? So another way to look at this would be so it was just now it was expectation of x squared 1 minus x and then over 1 over 1 minus a, where your x is uniform a to 1, okay? And this means this is basically just 1 minus a expectation of x squared 1 minus x, okay? And of course, then your Monte Carlo estimator will be just, you can take out 1 minus a here, it's a constant. So xi squared 1 minus xi over n, okay? Where your x1 until xn are IID, uniform random variable between drawn from a to 1, right? So you can see that with this new estimator, right, the variance will definitely drop because first thing, your values will not contain, so your values will be ranging from, if you put in an a here, so for example, you put an a here, multiply, you basically just have a bunch of numbers that are just going like this, okay? Rather than, let's say you have a range like this and then you got a bunch of zeros here, right? So definitely you already cut out the variation across here, right? So definitely this way of constructing a Monte Carlo estimator will be have a better property in terms of the variance. And in fact, if you want to do an analysis of the upper bound, right? The upper bound of the two estimators. The first one just now was, let's say MC1. Just now that one was the following. Okay. Where this one, the X are uniform 0, 1, right? The second one is this one, right? 1 minus A and so your X is uniform A1, right? So they're drawn from different distributions, right? Okay, so so for this one, we know that its variance is bounded by theta, then m minus theta, right? Where your m is equal to the max of over your x. So your x here will be between A and 1, right? Max of your hx fx over gx, which is this thing here. Okay, these things, right? So you want to find the max of this 1 minus a x squared 1 minus x, right? And this is very easy to find by direct calculus, right? If you use a simple calculus methods, take the derivative, right? 1 minus a you can take out, so x squared 1 minus x is equal to 2x minus 3x squared equals to 0, okay? And you do factorization, so you will get this thing. So your x is equal to 0 or x equals to 2/3, right? And clearly it is 2/3, okay? Right? So for max, okay, you can actually check the second order derivative, right? d2 dx2, okay, of 2x minus 3x squared. Actually, this constant here is not important for maximization, right? Because it's just a constant here. So this will be 2 minus 6x, right? So if you put in 2 over 3 here, it will be 2 minus 6 times 2 over 3. That will be negative, right? Okay, so the maximum occurs at x equals to 2 over 3. So therefore, your m is equal to 1 minus a times 2 over 3 squared times 1 minus 2 over 3. And that's 1 minus a 4 over 27, okay? Right, so I know that this one will be something like theta 1 minus a 4 over 27 minus theta, right? So this is its upper bound, right? Now, how about the upper bound for this guy? For this guy, right? So you can actually similarly find out as follows. Okay. So over here, you want to find the variance of theta hat MC1, right? So which is the same as 1 over n times variance of this thing. Okay, so so this will work out as follows. So basically, then you need to concentrate on this part here, right? So actually, this part here is actually for the term here because both of them actually have. Let me see. Over this side here, the analysis over here, it actually has a 1 over n, right? But we just ignore that because this is basically just a consequence of how many sample size you draw from, okay? Of course, you can reduce it by increasing n, but this part is important, right? So we focus on this part. So here, you have the expectation of this squared minus the square of the expectations, okay? So this is already known. This is basically just your theta, right? So this is just your Monte Carlo estimator. So the expectation is theta. So this is theta squared, right? So then you need to evaluate this part, okay? Now this part here is basically the integral from this okay? And this one you can actually split it into two parts, right? So, so basically because it's a square, so you can split into two parts, okay? And after that, let me make some space here. So after that, you do the same. So over here, you can see that this is bounded by the max of this part, okay? Okay, this function, right? This is some function, right? It's definitely bounded by its max, right? So this part you replace replace it with the max, and then you have less than or equals to times x squared. So this part you keep, okay? And as we saw just now, the max is 4 over 27, okay? So this becomes 4 over 27 integral of this, okay? And dx, right? So this becomes this becomes 4 over 27. So this is basically just the Monte Carlo estimator. So it's just theta, right? Okay. So therefore, this variance of this thing I can write it as less than or equals to 4/27 theta minus theta squared, right? Just like how I did it for MC2. And basically this one you factorize, it becomes something like this. Okay. Now if you compare these two variances, right? Okay. So you compare this one and this one, right? Okay. So which one should be, which upper bound is larger? This one or this one? The upper bound for MC1 is larger or upper bound for MC2 is larger? Anyone?
MC1.
MC1, right? Because your MC1 is 4/27, right? MC2 is also has 4/27, but it's multiplied by another number, 1 minus A. And if your A is close to 1, right? This is actually a very small number. So definitely the variance of MC2 is much smaller than the upper bound of MC2 is definitely much smaller than the upper bound of MC1, right? And this agrees with our intuition for these two cases, right? If you use MC1, you have this case, okay? MC2 is only this part, okay? So its variance should actually drop, all right? Okay, so this is the basic idea for importance sampling. So now I'm going to show you a simple demonstration using R to compare these two things, all right? Okay, let me just share the R console, okay? So let me see. I should share the desktop. Okay. Okay. So in the first case, let's say I will simulate this 10,000, right? You can simulate as many as you want. Okay, as many as your computer can take, but usually around 1 million something should be okay, right? So the first one is I'm going to draw my x from uniform 0, 1, right? And the first estimator, let's say I put gx, will be x squared times 1 minus x. And then this is the indicator function, right? So this is x greater than some a, okay? So this part here plays the role of the indicator. This is in R, this is a logical checker, right? For example, if you put 1 is greater than 2, it's false, right? Okay, so when you put a statement in inequality like this in R, it's a logical checker. So this actually represents nicely the indicator function. So of course, A, I have to put some constant, like for example, I put say 0.8, right? Close to 1. So then the other estimator, let's say I put Wx, right? Actually, to avoid confusion, maybe I just put something like Vx and Wx, okay? To avoid confusing you with the Gx. So this one is x squared times 1 minus x. Don't forget the constant, right? The constant, there was 1 minus a, right? Multiplied by that, okay? Sometimes you may actually forget the constant, okay? And then this one, okay, this one actually is not, this should be y, where your y is actually uniform a to 1, okay? So you should put the A first before that, right? All right. So basically, this simulates the this simulates all the values in theta 1, and this simulates all the values in theta 2. So Monte Carlo 2, MC2. Okay. So you want to find the estimate. So let's just try mean of Vx and then mean of Wx, right? Okay, so you could, oops. So you could run the whole thing. Okay, so you can see that their mean is about 0.015, right? They are quite close. And then the interesting part here is to compare their variances, okay? Let's compare their variances. All right, so you see a big difference here, right? The variance of the method, the estimator derived using the importance sampling is so small. Okay, 10 to the power of minus 5 times 5 point something, right? So you could actually see the percentage of reduction, right? So you take the variance of Wx relative to if you don't do anything. You look at that, all right, so the ratio is 0.04, okay, about 4.7%, right? The variance of the estimator derived using importance sampling is only about 4.7% of the variance that you obtain using the direct method, right? So what's the percentage of reduction in variance relative to Vx is how much? Can somebody answer me? Anyone?
4.66.
This is a percentage of reduction. 4.66 is your variance of Wx is 4.66% of your variance of this Vx. So if you're going to talk about percentage of reduction, do you read directly from this? Yeah, okay. Suta Veni says it's 95.3%, right? So you have to take the complement, right? So you take 100% minus 4.7%, right? So that's 95.3, okay? So when you look at the percentage of reduction relative to Vx, after you calculated the proportion of these two variances, you have to take the complement, okay? So you see that it has a relative to your V of x, right? You manage to drop the variance by close to 95%. So that's a lot, right? And that tells you that that's why you have to learn importance sampling methods, because this is one of the methods for variance reduction, and is particularly useful when you need to evaluate integrals, right? That for some reason it's actually not starting from the natural support of that of the random variable that you can easily generate. Okay, like for example this one, right? It's starting from a, it's instead of starting from 0. Okay, so this is another important method in variance reduction, in addition to the other two that you learned, right? Antithetic variables and control variables. Okay, so importance sampling is also pretty cool, right? So this is one example, and I'm going to show you another example. Let me go back to the whiteboard. Okay, so another example using some very familiar okay, some very familiar situations. So maybe I create a familiar situation like this. Okay, so suppose let me change the color a bit. Okay, suppose you want this integral. Okay. Maybe something like 1.96. Can somebody tell me what is this value? What is the value of this integral? Anybody? Hey, you're all statistics students, yeah? You see this integral, you have to have some very intuitive, you should have some intuition about this value. Okay, Hafiza, all right, that's good. So basically this is just, this is standard normal, right? This is your standard normal density, right? So basically this is just asking for the area under the curve for 1.96, isn't it, right? And you have done so much problems in statistics that you know that your 95% confidence interval is what? Plus minus 1.96 times your standard error, correct? For your mean, right? So 1.96, so this is 95%. So the 1.96 should be very kind of like some magic number for you, right? So this should be 0.025, okay? All right, so this is your statistician's intuition, right? If you ask some people who never studied statistics, they look at this, they will feel that this is a very complicated integral. But if you study statistics, this should appear to be very easy, okay? All right, okay, so we know that intuitively this is 0.025, all right? Okay. Now, how do you go about doing a Monte Carlo case here? So, okay, so you could actually write like this. The naive Monte Carlo case will be like this, right? 2 pi indicator function x greater than 1.96. So this 1.96 plays the role of a here, all right? So dx, okay? So now, so you got to introduce, in order to use the Monte Carlo method, you got to introduce something like some density here, right? Which is, so here you have 0 to infinity. So one possible candidate is the exponential, right? Okay. So you can introduce an exponential and then cancel it. So introduce exponential and then you cancel it, right? Okay. This is your exponential one, okay? So this guy here, so you will group together. So this will form your hx, and this will be, of course, your density, right? Fx, which is nice sampling between 0 to infinity, okay? So then you can write this as the expectation of so this thing will be e of minus x squared over 2 plus x over square root of 2 pi, right? Where your x is exponential 1. Okay? So therefore, your Monte Carlo estimator here will be summation 1 over square root of 2 pi is 1 to n e of minus xi square over 2 plus xi, where your xi, and then forgot the, let me see, I forgot the indicator function. Okay, so should be like this. Indicator function x greater than 1.96. Okay. Indicator function xi greater than 1.96. Okay. Where your xi are ID exponential 1. Right? So this is one way to do your Monte Carlo estimator. Then we do this importance sampling, right? So let's do the importance sampling now. So how are we going to do the importance sampling here? So let's see. Okay. So my data, I can write it as so you need to introduce first from here, right? So you need to introduce some gx, right? And this gx has to be similar to your, to your density here, e of x, okay? So a natural candidate is to use a shifted exponential. You see, because you're integrating from 1.96 to infinity. So you have a shifted exponential that is starting from 1.96, right? So instead of an exponential that is like this, you do an exponential that is like this, okay? Right, shifted exponential, okay? So over here, before 0.96, it's just flat, right? It's just shifted by an amount 1.96, which corresponds to here. So you will write it like this, okay? So you just follow here, e minus x squared plus x. Right, so now your so that will be, so you have to take the whole thing. Let me see. Okay. Now you introduce a shifted exponential, so that will be minus x minus 1.96. Okay. Right. So because over here your x will be starting from 1.96. Okay. So let's look at this carefully. So this is your gx. This part here is your hx. This part here is your fx. Okay. And then of course your gx, you have to multiply it again here, right? Because you cancel off. Okay. So I'm not going to write this down. Okay, it's just gx, right? So then this becomes, so you can cancel these two things here. And then this x and minus, you can get rid of them. So it becomes this square root of 2 pi times this, okay? X minus 1.96 gx dx, which is e of minus x squared over 2 plus x minus 1.96, okay? Gx dx, right? So this will be the expected value of the following. 0.96, where the x is shifted exponential, okay? All right, okay. So then your Monte Carlo estimator for the second one will be 1 over square root of 2 pi summation e minus xi square over 2 plus xi and minus 1.96, where your x are, sorry, forgot, there's divide by n, right? Okay, divide by n. So where your x is shifted exponential, right? Okay, so let's look at the R implementation. Okay, so I have less than a minute now, so I'll stop here and then restart another meeting. Okay. All right. Okay. So we need to. Okay. So we will try out our ideas just now, right? So again, my n is the same. Let's say 10 to the power of 4, and my a is 1.96 here, right? So the first Monte Carlo estimator that I have to do something like this. Minus, let's say I put gx, x squared over 2. Before that, my x is drawn from exponential 1, right? This is plus x, and then I have so this thing is divided by square root of 2 pi. Okay, and then you have the indicator function, right? Times x has to be larger than your a. Okay, and then let's say I call again. This is let's say vx. This is wx. Exponential minus x square. Sorry, it's y square over 2 plus y minus a. Where my y is r exponential n1 plus a, right? So this is your shifted exponential, okay? Right? So, and of course, don't forget the square root of 2 pi, okay? Right? So then I will check the mean of Vx and then mean of Wx, okay? So let's try to run the code. Did I? Oh, I forgot something here. So here there is actually e power of 2 plus x. Did I leave out something here? The first one, Vx.
X should be in the bracket. The last term.
At the end of the equation.
Time. Oh, okay, right. Thanks. Okay, x larger than a, right? Let's try to run this again. So of course, you understand that every time you run this, you will get a different, slightly different values, but they should be more or less the same, okay? Because you all understand the reason, right? This is the seed number, right? Every time you run this, unless you set a seed, right? And you know that the seed number is basically when you do the linear congruential generator, the seed number is your initial starting value, right? So basically that's why you use a different starting value, you get a different sequence, okay? Thus, if you don't set the seed number, every time you run it, I think what R does is that it will kind of like take your clock, your computer clock, right? So it will take every time you run it, it will be different. Your time is different, right? Your timestamp is different. So that's why you get a different number, okay? So it takes your date and it adds up those numbers and create a new number, okay? So that's why every time you run it, it will be different, okay? So, okay, you see that over here, your mean Vx and Wx are very close to 0.025, right? Okay, so that is one sign that this is okay. Then you check the variance, okay? Now, the variance that you get from the naive Monte Carlo method is 0.006 something, right? The one that you get from importance sampling, look at that. It's 0.003, right? It's more than 10 times. Relatively, it's like a factor of 10, right? It's something like divide by a factor of 10 and then half it. So it's something like by a factor of 20 smaller. So of course you can get it more precisely. So W, you just divide it, Wx over variance of Wx, sorry, Vx. So this is 0.0595, right? So your new variance is just about 6% of the variance of the naive Monte Carlo estimator. So you managed to achieve how much of reduction relative to the naive estimator? Anyone wants to answer that? The amount of variance reduction is about how many percent? Yeah, okay, 94%, right? All right, so it's very powerful, you see. So once you, in fact, if you use this method, right, you could calculate its 95% confidence interval, all right? So definitely for the same sample size, your confidence interval obtained using the method of importance sampling will be much smaller than the confidence interval that you obtain using the naive Monte Carlo estimator, right? Okay, so I think with these two examples, right, you should have some it's actually not that hard, okay? Initially, maybe the first example that I use is it's following some textbook, but then I found that actually this other examples may be easier to understand rather than that example. Okay, especially this second example where you are familiar with the integral. So, all right, okay. Any comments from you? Your understanding of this method is okay? Right? The R codes are actually fairly straightforward. As usual, you basically just need to specify the sample size. And here is your constant, right? And then the rest are just basically the distribution from which you sample from, okay? So, and then this part are just your representation, right? The summon, the summon in your in the summon in your Monte Carlo estimator. So, and then that's it. Very straightforward. Find the mean. This one is just to confirm that your Monte Carlo estimator is estimating the right thing. And the important thing is to compare the variance. Okay. Some questions here. Which of the okay. The textbook thing, I think the thing about the textbook is that you see the textbooks that are available, right? I'm actually using some of them. You can't find them because they are with me. Okay, and the library only has one copy. The thing is that these textbooks, they sometimes talk about things that are not really what I want to talk about. Okay, they talk about things that are a little bit going a bit away from the course content, right? So, and then sometimes the examples that they use are a little bit complicated, and I don't think they are that useful. That's why there's no single textbook that is really like something that you can follow. Okay, and this actually happens a lot for third year courses, right? Because third year courses usually up to senior level, the kind of things that people think are important, they change, all right? And depending on whether the book was written in the 90s, 2000, 2010, the focus will actually change slightly. So that's why there's no single textbook that that you can actually follow from beginning to the end, right? So that's why I think I talk about the things that I think you should know, and then of course my initial idea is for you to make the notes from my slides, right? But then I also realized that maybe that might be difficult for many. So that's why I said later I will compile some notes and put it up on Spectrum. Those are the things that you can follow for this course, right? Of course, you are free to read some of these notes from other universities, but again, I said different universities, right? Their lecturers, they demand different things. Okay, depending on the preparation of the orientation and the preparation of the students. Sometimes they go very narrow but very deep. Sometimes they go very broad but not so deep, right? So, okay. The syllabus, you can look at the pro forma, right? Basically, the syllabus, the kind of topics are there, but then of course, it's very general. Okay, so if you look at the pro forma, let me see. Screen sharing. Okay, let's see. Teaching schedule. Okay, this is the original one, right? So we covered this, right? Introduction, calculation of integrals, right? So 2, 3, computer generation, we already talked about that. Uniform, non-uniform, okay? Variance reduction, okay? We're talking about, so actually, in fact, variance reduction is taking more time than expected, all right? Okay, so basically we covered here, so the things that we talked about for last week and this week are, they are to do with variance reduction, okay? Then we're basically done with this part already. There actually like additional stuff in this chapter. If you follow the other books, it's actually quite a big topic, variance reduction. But I think we for this course for this semester is enough that you study up to whatever we covered until today, right? Then from next week onwards, we'll just do bootstrapping and jackknifing, all right? And they relate to so this one actually we can cover quite quickly, right? The theory is actually the algorithm is actually quite simple. And then there's something on permutation tests, all right? Which I will talk about later, all right? So next week we'll, actually I think we don't need 3 weeks for this, maybe 2. Okay. And then after that, it's a maximum likelihood estimation using this particular algorithm called EM. Okay, and then after that, it's very quickly to some more advanced method for simulating variables. That's called Markov chain Monte Carlo method, right? This one we the implementation is actually quite straightforward. Okay, so the code is actually already there, so you just need to roughly know how to tune the algorithm, and that's only 2 weeks for that, right? So okay, so basically that's the content, right? EM may be a little bit it's actually not that hard, okay, EM. And this EM, right, is actually not in the textbook. It's actually a chapter in mathematical statistics, right, for a lot of textbooks. Then for a lot of these kind of simulation textbooks, they don't include EM. Okay, that's why I say there's no single textbook that is the best, right? We take the good ones from every book and make it into a course. Okay. All right. Okay. So that gives you some idea, right? Are there any other queries? Doctor, for the first example, how do we get A? Now, this A is some value that you want to, it's up to you to set, right? It's not something that you find, it's something that you want to, it's just some value that you want to evaluate, that's all. So, like for example, suppose you just want to evaluate some function from whatever, okay? This A is up to you. So this is what we call a tail, right? This whole thing is called a tail probability, right? Because it involves some function. You want to find the tail, right? You're not interested in this part, right? But you're interested in the tail, okay? So how what A should be is entirely up to you. Generally, this in statistics, this is related to the calculation of p-values, right? Because your p-values usually are the tail. Your p-values are basically the tail probabilities, all right? Where your A is basically the observed test statistic, right? So that's in the context of an integral in statistical testing. Okay. All right. Okay. So are there other questions that you want to ask? If not, I also quickly go to tutorial 3. I hope you have tried tutorial 3. Let me see. Desktop. Let me see. Tutorial 3 is here. Okay. That's assignment 2. This tutorial 3. Okay. All right, so tutorial 3, you basically have this is actually quite similar to, let me see. So this is your algorithm for generating the discrete uniform, right? Take the integer part of NU, where your U is, that's why you see uniform random variable, although it's simple, right? It is so important because it forms the basis for the other kinds of non-uniform random variables, right? How do you generate non-uniform random variables? They all go back to the uniform 0, 1, right? Including the discrete, okay? So this is very beautiful. So basically you want to show that the mean and variance of X, right? They conform to those of the discrete uniform, okay? So you look at the solution, right? Later I'll post this up, okay? So, all right, so basically your integer NU, first you have to figure out its range, right? So this is very easy. So your U is between 0 and 1, so your NU is between 0 to N, right? Therefore, the integer part of NU is 0, 1, 2, 3 until N minus 1, right? Because your integer part is the part that is consisting of the integer, right? Like for example, you get 0.1, the integer part is 0, right? And so you can't go until N, so the integer part will be N minus 1, right? So this is clear. And therefore, your X equals to integer NU plus 1, it will range from 1 to N. All right? So from here, you just add 1 to all these values, right? And each of these values is equally likely to occur, right? You don't, because it's a uniform random variable, so whether you get which integer is equally likely. So therefore, the expectation of X is just basically 1 times 1 over N, then you add up everything, right? So this is again very simple arithmetic sequence. So it's N over N plus 1 over 2, so you cancel off the N, you get N plus 1 over 2, right? And then the expectation of X squared is the same, right? So this is the sum of squared numbers. So it's N plus 1, 2N plus 1, okay? So the N cancels off, so you get this term, right? So the variance is, after you do some math here, you get N squared minus 1 over 12, okay? And this one you can check with the statistical properties of the discrete uniform, right? They are actually the mean and variance of the discrete uniform over 1 to N, okay? That's the theory lah, right? And then you have the second question on second question is on okay, let me see. Second question is on the geometric distribution, right? So you're asked to find this estimate, okay? Using 1 million IID geometric random variables with theta equals to 2/5 and then find its thing, okay? How close is this Monte Carlo estimate to the true value of S? Use the SIT number. Yeah. Okay, so let's look at the solution. Right, so the first thing that you need to know is you are interested to find this okay, so you want to find the sum of 1/n plus 1 square, right? Now you have to express that sum in terms of some kind of expectation, okay? So the trick here is to you introduce the geometric density here. So these are the densities from the geometric distribution, right? So actually it's here, right? Okay, so this is the density and you cancel them off, right? You introduce and you cancel them off. So basically this this representation is basically just the sum of that reciprocal squared integers, okay? But once you write it in this representation, you can actually group them, right? So you treat this part here as the density, and then this part here will be its expectation. So it's so those values drawn from this density, right? So that's why you can have the expectation. So this part here will be the expectation, right? The whole thing will be an expectation. Okay, where this part here, then you can this whole thing here, this whole thing here, you can actually write as this part here, right? The 5/2 is a constant, so you can take out. Okay. So here, this corresponds to a geometric distribution with theta equals to 2/5, right? This is theta. This is 1 minus theta. So possibly the only tricky part is how you can actually write the sum in this form, because it's a bit tricky because you got to introduce and then cancel off, right? But once after you introduce, you do the grouping, right? Then you can express it in this expectation, okay? And once you have this expectation, things are easy because your x is basically just drawn from the geometric distribution, okay? So then you have this, and you just draw from the. Actually, this is a x. This is actually a typo. This is actually x sub I. Okay. So then basically you use the SIT number, you will get this, right? So this is the implementation. All right. The code is actually just recycled from the previous weeks. All right. You just need to specify the GX, specify the distribution from which you draw the x, and then that's it. The Monte Carlo estimate and the confidence interval. Okay. You find that this value is 1.62 something with a lower end of 1.599 and upper end of 1.64 something, right? This, of course, the true value is pi squared over 6. So it's very almost equal to that value, okay? So this is actually a classic result, right? So it's a classic result. Okay, summation of 1 over n plus 1 squared n equals to 0 to infinity is n squared n 1 to this. This has a classic result, pi squared over 6. All right. So, and that this one, of course, can be obtained from analysis, right? From real analysis. You can actually check Wikipedia. It shows you how to do some clever tricks to get this from analysis. But the idea here is how to evaluate this from a Monte Carlo perspective, right? So basically, this part here, you introduce so this is your n, right? So this is your geometric density, right? So density, and then you cancel them off, right? So that will be theta minus 1 minus theta power minus n, right? So basically this part is multiplication. This is basically 1, right? So you're not doing anything illegal. But once you have this operation, right, it allows you to do the grouping. So this is one part here multiplied by a density, right? And this allows you to express it as an expectation, okay? Expectation of, so then this is treated as a random value from this density, right? So could write this as x plus 1 squared, okay? Minus x, okay? Then where my x is having this density, okay? So that's the idea, right? That means all this kind of whatever sum that converges, right? You can also use a Monte Carlo framework to actually find them, okay? So, okay, so that's the general idea, all right? And of course, you can always improve them using variance reduction methods. Right, okay. So then I talk about, let's see the other questions. Share desktop. Right, so this is then describe an algorithm to simulate this value. So this is actually quite straightforward, all right? This is basically just 110, 210, 310, 410, right? Then after that, use the SIT number. This, if you can do this, then you can do your assignment 2 question, right? So, okay. So this one, if you look at the solution, right? So solution is very simple. So you generate uniform 0, 1, right? If your U is below 0.1, you just set as 1. Okay. Now note very carefully, right? In this case, you are starting, your I is 1, 2, 3. If your starting value is 0, then this one you set as 0, yeah? So just be careful, right? Else, now why is it 0.3? Because the first one is 0.1, the second one is 0.2, right? So you cumulatively, you get 0.3, right? So this part has to be the cumulative, right? And then this part is the cumulative, okay? 3 plus 2 plus 1 is 6, right? And you only need to do until the first 3, because then if it's not the first 3, then it must be the 4th, right? By complementation, okay? So this is very easy, right? And this is the R code to do the conditional if, right? So this gives you some framework, okay? And this part here is basically just to do the simulate 1,000 times, okay? And then this is the chi-square test. You do the chi-square test on the table, right? You can tabulate the results. You can actually type table Y to see the tabulated values, okay? And this is the way you do the chi-square test, right? Okay. if you set the SIT, your p-value will be, you should be getting a large p-value, because if your simulated values follow the distribution that you try to simulate, then there's no, the fit will be good. If the fit is good, the p-value cannot be small, because the small p-value means that your observation is conflicting with your hypothesis. Okay, in this case, when you do everything correctly, it shouldn't conflict, right? So you should expect to get a large p-value. Okay, and then for number 4 is basically simulation of negative binomial random variables. And this one is actually similar to how you would simulate Poisson and binomial. Okay, basically you just need to find out the recursion identity. So you work out the recursion identity first. Okay, so do some algebra here, you rearrange, you will get this recursion identity, right? And after that, you basically just follow the algorithm that you use to generate Poisson or the binomial random variable. Okay, these steps are the same. Okay, just remember that your updating, right, has to be sequentially like this. The final K, the update of the K has to be done final, not before. Yeah. So this one, your K update to K plus 1 cannot be done, cannot be written here, because when the computer executes the line of codes, right, it follows what we call imperative execution. So the first line will be executed, followed by the second line, and so on. So the sequence of this order command is actually important. Yeah. Okay. So please take note. Okay. So basically, this is for generating negative binomial, and this is for checking, right? In this case, another way to check is to use the bar plot. Okay. So you can check the bar plot, and it will look like this. Okay. The gray color is your, let me see, okay. So the true value is in red, and the gray color is in the observed one, right? So you see that your observed, if your observed and the expected probabilities are about the same, then you don't see much of a discrepancy here, right? So these are some discrepancies, right? So this fit is actually quite good. Okay, you will not get a perfect fit because you are doing simulation, right? So